Alright, I just have a term out front, and I need to multiply it to two terms on the inside. So it looks like we're going to have properties of exponents here we got to work with. But let me write it out part by part. So I have 2, just the number 2. I've got a y to a 1/3. It's going to be multiplied by a y, and it looks like that one has a first power on it. Okay, then I have y to the 1/3 and y to the 1/4. Okay, so if we clean this up just a little bit more, remember if I have the same base and I'm multiplying, I have to add my exponents. So a 1/3 plus 1, you can convert that 1 to a 3/3. So 1/3 plus 3/3 is 4/3. And then right here, I have the same base and they're multiplied. So again, I'm going to add my exponents. So what is 1/4 and 1/3? What happens when I add those up? Okay, obviously a common denominator of 12. So it'd be 4/12 plus 3/12, which is 7/12. Okay, and what I want to tell you guys right here is basically what I said in the last problem we just did right above this, is that anytime your variable is what has a fractional exponent, you can leave it just like that. You don't have to worry about reconverting those back into radicals and going from there. If that number out front, if a number is your base that has a fractional exponent, like right up in here, we want to go ahead and try to clean that up. But if you have a variable that has a fractional exponent, just leave your exponents as is. So really, this is our overall answer, because the only thing that has a fractional exponent are variables, and we don't have to worry about those yet. Okay, so let's go on to example number 8. With example 8, really our goal here, the purpose of this one, is just specifically to look at what do we do whenever something doesn't come out perfectly. Like we've been always doing the cube root of 8 or 27, and that came out perfectly, it was 2 or 3. Or we did this, square root of 25, which was 5. But what happens if we don't have stuff that works out perfectly? What do we do in that case? This is what example 8 is all about. And what I would recommend is, first of all, think about it in two different groups. Think about it as the number, and then think about it as the variable. So what I want to look at, first of all, is the square root of 40. Okay, and then we're going to take care of the variables here in just a second. So we kind of have like a set of rules to do the number and a set of rules to do the variables. And what we want to do with 40 is we want to break it down. We want to factor it. And what we're going to factor it to, let's look at it. So you can either do 40 as 2 times 20. It could be 4 times 10. Or, roughly that's pretty much it. Other than 1 times itself, that's pretty much it. Well, what you want to do in order to pick which one do I go with is looking in that list, of any number up there that you can take a square root of. Well, obviously it's 4, so we want to go with the pairing of 4 times 10. So let's write this now as a square root of 4 times 10, and then we'll have times a cubed and then b to the 4th. Okay, so whenever I'm solving this, what I like to do is leave myself some room, because there's going to be stuff that's going to come out front, and then stuff that's going to stay inside that radical. So let's go part by part. Like how I wrote it as 4 times 10 times a cubed times b to the 4th. So first of all, what's the square root of 4? Well, the square root of 4 is 2, so let's pull that out. It's definitely a 2. So that can go out front. And then the square root of 10. Well, we already decided can't do much with that, so that's going to stay inside. Okay, so what I can take the square root of, I'm pulling out, and what I can't, I'm leaving inside. All right, that took care of the number part. Now, how we're going to do the variable, this is what's different. Okay, what we're going to do is go to this index number sitting right there, which is a 2 because it's a square root, and we're going to divide 2 into our exponent. So how many times does 2 go into 3? Well, 2 goes into 3 one time with the remainder of 1. So what are we going to do with these two numbers right here? The one being what we divide into, and then with the remainder. Well, however many times the index goes into that exponent is the exponent on the outside, and the remainder is the exponent on the inside. Okay, just like that. So now let's go to the b's. How many times does 2 go into 4? Well, 2 goes into 4 2 times perfectly, so it's b squared. And if I wanted to, I could then write 0 on the outside, in the inside, because there's a remainder of 0, which we learned from up above that anything to the 0 power is just 1, so it's just going to be 10a inside, and that's our answer right there. Okay, so just before we go on to this next one, if we wanted to get just a little bit more practice, let me kind of erase this just over here on the right, and if I just wanted to work with just the variables one more time. let's say I wanted to do the cube root, let's say a to the 5th and b to the 10th. Let's try that. Okay, so first of all, set yourself up a cube root. We're going to throw stuff out and leave stuff in. How many times does 3 divide into 5? Well, 3 goes into 5 one time with the remainder of 2. How many times does 3 go into 10? Well, 3 goes into 10 3 times with the remainder of 1. And so that kind of gets you just a little more practice on working with those variables. Again, when you have a number, just do the number as is. But when you have variables, you do the whole division thing, the index into the exponents. Okay, going to the next one, we have the cube root of 64. Well, 64 is definitely not a perfect cube, so what can I break this down into? Something I know I can take a cube root of times something else. Let's go over here to the side. Let's say 64. I know that's a product of specifically, 8 times 8. What's half of 64? It's 2 times 32. See, does 3 go into it? Not so much. And then we can maybe choose 4, because it'll be 4 times 16. Okay, so in this list right now, we pretty much are looking at all the different quote-unquote factors of 64. And if we go up there, we want to look for something that's perfect cubes. Well, look right here at this very first listing right here, 8 times 8. Well, 8's a perfect cube because 2 cubed is 8. 2 times 2 times 2 is 8. So since this one, the first 8 is a perfect cube and the second one's a perfect cube, then what that means is that 64 right from the start should have been a perfect cube to begin with. So let's think about that. We know 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Let's go to 4. 4 times 4 is 16. 16 times 4, there you go, 64. So actually, 64 is a perfect cube to begin with. So let's write ourselves a blank cube root, and let's start going piece by piece and seeing what we can do here. So we said the cube root of 64 is 4. We're going to pull the 4 out front. All right, let's go with our variables. We're going to take the index number of a 3 and divide it into each of these exponents. Well, can 3 go into 2? Not at all. You have to have at least 3 of something. So those x squareds are just staying inside as is. Let's go to the y's. 3 goes into 4 just one time with the remainder of 1. Let's go to 11. 3 divides into 11 3 times with the remainder of 2. And there's our answer. If you want to write this without showing the exponents of 1s and just write 4yz cubed times the cube root of x squared yz squared, that's totally fine. Now if you want to leave the 1s in there, that's even perfect. And all I can reiterate is the fact of make sure that if you have a radical that's not a square root, make sure you always incorporate that index number. A lot of times people forget to put that in there, but if it's not a square root, you have to define it as something other than a square root. Okay, let's go on to the next topic.